All right, so encryption is a very important topic in network security. So in the internet or in any network, we use encryption to provide confidentiality. And most of the time, security people don't want to learn cryptography. They just ask cryptographers what is secure, and they say some algorithm names and they use it. But these algorithms actually use some parameters, or you need to choose some mode of operations. So most of the time, people who don't know cryptology actually chooses these parameters wrong. So today's topic actually is to briefly cover important topics in block ciphers. So let's start why we need cryptography in the first place. So our famous people, Alice and Bob, in Turkish we generally refer to them as Aslı and Barış. So they want to communicate through either wired or wireless communication. So you can think about anything about the internet or anything we covered throughout this course. So we always assume that this communication is insecure because somebody can always tap in, right? If it is wireless, it is very easy. Eve just has an antenna and listens to the communication. So we always assume that the enemy or the Eve always listens to this communication and records it someplace. So this is a passive attack, right? Because you don't know that you're listened. But if Eve has more capabilities, you can modify this data that is going through this communication channel. So she can delete or modify or add new stuff, right? So we still want to communicate in a secure way through this insecure channel, okay? So our aim is to provide algorithms that will provide us confidentiality, which block ciphers will provide, but we also need integrity, authentication, and so on. So we will cover these topics with hash functions, authenticated encryption, public key cryptography algorithms, and so on and so forth. So for instance, if they want to communicate, they need a secret key, but for instance, Bob can be a website that we want to buy something, right? So we haven't talked to them before, and so we couldn't exchange any secret keys in a secure way. So we can use even algorithms like Diffie-Hellman key exchange, where these two people can agree on a secret key through this insecure channel, where Eve cannot understand, even she listens to the communication. But first, we talk about block ciphers or then stream ciphers to see why we need a secret key. Then we will talk about how we can create this secret key or agree on a secret key, okay? So let's start with encoding. Historical ciphers mostly operate on letters since they are pen and paper methods, but nowadays, we moved on to machines than to computers, so we work on digital data. When working with digital data, we can represent letters, numbers, symbols, etc. as string of bits, okay? We can store bits, we can transmit bits. This is why we are always dealing with bits, zeros and ones, okay? Thus, the communicating parties must first agree on an encoding, right? You can represent your characters in ASCII format or UTF-8 if you are using Turkish characters and so on and so forth. So we first agree that communicating parties understand each other. Okay, there is an encoding. This is important, but it's still an issue even in 2023. Some people don't use Turkish characters when sending emails because it appears in a weird way in some people's inbox. So at this point, just assume that we know what an encoding is and we understand each other. So cryptography is a very big area and it has a lot of areas and newly added areas. So this was an incomplete picture I drew years ago to show that it doesn't only consist of block ciphers or algorithms like RSA or Elgamal, okay, or Diffie-Hellman key exchange. So books generally divided into two, saying that there's symmetric cryptography algorithms like block ciphers, stream ciphers. These are encryption algorithms. There's also message authentication codes, which is not an encryption, but provides authentication. Or asymmetric key cryptography algorithms like digital signatures, key exchange algorithms, or encryption algorithms like RSA or Elgamal. But cryptography is not all about this. We have keyless algorithms like hash functions. We have an area called randomness, which is very, very important because almost in every step when we write a cryptographic algorithm, in the pseudocode, we say randomly generate a number or randomly choose a prime number. So you need to be sure that how you do it in a random way, okay? But the topics are really broad. We have lightweight cryptography, post-quantum cryptography, homomorphic encryption, multi-party computation, and so on and so forth. So there are many topics that needs to be covered, but we can only focus on some of them. But don't forget that the picture is really huge and new areas are added every day. We didn't have post-quantum cryptography maybe 20 or 30 years ago, but now we are talking about it. Or homomorphic encryption was just a dream because it was impossible to achieve. I mean, the algorithms that we had when you used, when you encrypted a few bytes, the ciphertext would end up to be a few terabytes, which would be impractical, right? Nowadays, we have practical solutions and so forth, so on. So this is why we have always new areas to talk about. So this is another picture. This is not by me. So this actually explains a little bit more how the areas of cryptography are connected. So in order to provide confidentiality, we have very traditional algorithms like block ciphers and stream ciphers. So we are going to focus on this part today. But we also have public key algorithms that provide confidentiality like RSA or ALGAMO. We have authenticated encryption algorithms, which provides confidentiality, but also data authentication. ASCON is the new winner of, for instance, the NIST lightweight encryption competition. And it is also an authenticated encryption algorithm. We have hash functions, which is very, very important, which you can actually use for areas other than cryptography, because it provides integrity. We also have message authentication codes that provides both data authentication and entity authentication, zero knowledge proofs, digital signatures, which solves the problem of non-repudiation. So we have to actually cover all of these to put in our discussion of network security, because in TLS we are going to need most of these algorithms. All right, so we already mentioned a few of these. We have sometimes keyless algorithms like hash functions, but we also have keyed algorithms like symmetric key algorithms or asymmetric key algorithms. So in the symmetric key algorithms, secret key algorithms, also they are called secret key algorithms, they use the same key material for both encryption and decryption, hence the name symmetric key cryptography. There are, okay, says 4, but it's 3 types of algorithms in this category, mostly block ciphers, which we are going to focus on, stream ciphers, and also message authentication codes, which is not an encryption algorithm, but it uses a secret key to provide authentication. Okay. So block ciphers and stream ciphers are encryption primitives, while the message authentication code is used for data and data origin authentication. But we can use a block cipher to build a stream cipher and a message authentication code and even a keyless hash function. So all of these areas, although looks independent, in order to understand all of them, we have to cover actually all of them and then look back to understand how they work actually. Asymmetric key cryptosystems are somewhat different. There are different types of algorithms here. For instance, key agreement algorithms like Diffie-Hellman. So in this case, 2 parties can agree on a secret key through an unsecured channel. Public key encryption algorithms, examples are RSA or ALGAMO, but we also have digital signature algorithms like DSA, digital signature algorithm, or standard ECDSA, elliptic curve digital signature algorithm, or we have Schnorr signatures, and so on and so forth. So let's start with some basic definitions. What is a cryptosystem or a cipher? So here we have plain text, which is what you want to protect. So this can be a file on your computer. This can be a WhatsApp message. Actually, this can be your voice when you are calling somebody. A cryptosystem or a cipher is a pair of algorithms that convert plain text to ciphertext and back. Okay, this is what we call a cipher or a cryptosystem. Ciphertext is the encrypted version of the plain text. Ciphertext should appear like a random sequence. So when you encrypt the plain text, this is what you send through this unsecured channel. So when somebody looks at it, they should see random looking bits, okay? And they should not be able to, obtain some parts of the plain text from the ciphertext. But the person you are communicating also have the secret key. They can, use the decryption algorithm and obtain the plain text back. This is the whole idea behind the cipher. So in the symmetric key crypto systems like block ciphers and stream ciphers, we have a secret key and somehow we exchange it within communicating parties, okay? So we just assume that we did it beforehand. So they have the secret key. So when I want to do the encryption, I use the secret key, and they also use this same key material. But sometimes round keys are in the reverse order, etc. But it's not important. This is the only secret part of the algorithm. If I give it to 5 people, the same key, we can communicate with each other, right? So they can decrypt whatever you send. But the important thing here is, again, the keys must be randomly generated. So this is the only part that we keep secret. So Kerckhoffs's principle says that even if the algorithm is publicly available, and actually it should be, the only thing you should keep secret is the secret key. And with that information, you should be secure if your algorithm is, good enough. So trying to hide and design is not a good idea, okay? You should provide it to cryptanalysts to check if it is really good, okay? And it takes years of, community work to analyze a cipher. So block ciphers operate on B-bit blocks of data. This is important because the data you are going to encrypt actually has a variable length, right? Because it can be 3 bits, it can be 3 terabytes. So designing an algorithm for all of it would be a hard task. So this is why we only focus on as if the input is B bits, because then we will combine, we will divide the plain text into B-bit blocks and then encrypt all of them. So each block is encrypted by a k-bit secret key to produce b-bit output. Output blocks form the ciphertext, which depends on the choice of mode of operation. This is very important. So when you use a block cipher, you also need to choose a mode of operation. This actually shows how you obtain the ciphertext blocks, how they're related. This is important because people generally use mode of operations like ECB, electronic codebook, which you can break in a very easy way. Thus, a block cipher and the chosen key is actually a permutation from 2B elements to 2B elements, right? So this is why actually in cryptanalysis we are trying to distinguish a cipher from a random permutation which just maps to the B elements to the B elements, okay? So there are actually a lot of ways to map these elements to the same sets, but the cipher is just a with every possible key that you can select is just a small subset of this huge space of permutations. Nowadays, we choose block size as 64 or 128 bits. If you have very lightweight designs, sometimes they can be 32 bits. But if you make it small, then you cannot use the same key for a very long time because you would be producing every possible output at some point. So you need to replace the key. And nowadays we choose key as at least as small as 128 bits. If you choose something less than this, actually you are not that secure. I mean, there are many algorithms like that support 80 bits, which actually makes no sense, which can be broken easily. But there are some algorithms which provide 112-bit security, which looks secure today, but we don't know how long it will be secure. So if it's a state secret and you want it to keep secret for 100 years, so most probably it is not a good idea to use that kind of security. And actually, when in the RSA, a lot of people use 2048-bit secret key that actually provides 112-bit security. And we will see this when we see public key algorithms. So for personal security, this is enough, but if you need military-grade security, then you need a key length as this. So there are 3 famous ways of designing block ciphers. One of them is substitution permutation network, like AES or present, faceland network, like DES, Clayfair, etc. Sponge functions are sometimes referred to as permutation-based cryptography. These are very popular. The ASCON is the winner of the new competition. But SHA-3 hash function is also a sponge function. Okay, you can also create block ciphers from hash functions from sponge functions. There are also types like arcs, addition, rotation, XOR. Generally, it may be fell into one of these places, so I didn't wrote it as a third or fourth step. So a cipher mostly consists of the repetition of a round R times. So instead of designing a very huge algorithm, you design a small part of it and repeat it. And that part actually provides two properties called confusion and diffusion. Okay. And we choose a secret key, right? But instead of using that secret key for every round, we actually have a key schedule algorithm. So instead of using the key directly in every round, a key schedule algorithm is used to generate round keys from the secret key. Right? So from a 128 bits, maybe you generate 3,000 or 4,000 bits that are used as round keys. So there are some design considerations because there are many different platforms. So algorithms have different performance or security in these platforms. So if you are going to design an algorithm for hardware, you can focus on bits because hardware implementation can easily work on bits. Since most programming languages focus on bytes, bit operations are more costly on software. Cipher design also determines the number of gates required to perform encryption on hardware. Number of gates determine the area required, and that actually determines the cost you need to build that device. So this is what is important in lightweight cryptography for Internet of Things, because you're going to build these devices, in a huge batches. So gaining 1 cent from the production will result a hell lot of cost reduction. Code size or required memory is not a big problem for software implementations due to fast CPUs and large RAM, right? Because we don't care about this. Even when students now with new programming languages, when they send their homework with the hello world, that only does printing hello world on the screen, their submissions becomes a few megabytes, right? But small code size is important for embedded software implementation. There are even devices with like 16 bytes of memory or that kind of designs. So code size or required memory is also important. So there is a trade-off between security versus speed. So you can add more precautions, but this will increase your security, but reduce your speed. So you are trying to actually find the sweet spot. Speed is generally measured as throughput. Adding more security measures, for instance, increasing the number of runs increases security but reduces the speed. Ciphers performing well on hardware or software may not be suitable for constrained devices for RFID systems or sensor networks due to limited memory, battery, or computational power. Hence, we also need lightweight ciphers. Okay, this is why in a few hours I will also talk about lightweight block ciphers. Okay, so let me show you the general picture of a SPN, substitution permutation network. So you have the secret key, and through the key schedule algorithm, you generate round keys, okay? So you have the plaintext block here. You add the round key to it, maybe simple XOR here. Then a single round consists of substitution, permutation, and key addition layers, okay? So this provides confusion, this provides diffusion, and this actually hides your step. So you repeat this round many times, and at the end obtain ciphertext. So idea is as follows. Even somebody captures a plain text and corresponding ciphertext, actually they cannot obtain intermediate values, right? Because at the beginning and at the end, you have a round key addition, which you don't know. So from here to obtain secret key doesn't look like possible, right? This is the idea behind using this kind of design. But of course, if the cipher is not designed in a good way, obtaining many plain text and corresponding ciphertext may allow you to obtain the secret key. This is actually what cryptanalysis focuses on. So let me show you a brief example. This is a present cipher. So it steps here as like you add the round key. So the block size is 64 bits. Each line represents a single bit. So round keys are also 64 bits. You XOR bit by bit at the key addition layer. At the substitution layer, we have 16 identical S boxes, which just maps 4 bits to 4 bits. Okay, so it is shown with the single table. Then we have the permutation layer or diffusion layer. So this actually maps bits to different places. So in the next round, you just take this picture and put it here and continue that way. You do it 31 times, and at the end, you add a final key addition here so that you hide your steps. So a basic design, as you can see, it fits on a screen. But of course, implementing it might take some time. Here's an example for a sponge construction. So these designs are a little bit different. And ASCON, for instance, allows associated data, which is data you don't want to encrypt, but you want to authenticate. Okay, so this is optional part. So in this picture, assume that it doesn't exist. So sponge constructions work like this. You have a huge internal state. In this case, it is 320 bits, and you initially fill it with IV, secret key, and nonce. Then you apply permutation to this internal state and mix it. Okay. After doing it for 12 times, again, this permutation layer contains S boxes or rotations and so on, which provides confusion and diffusion. Then you add your plaintext to the top, for instance, 64 bits to this internal state, and also provide the result as the ciphertext. So as you can see here, the input and output is just after the modification of internal state, right? So at the end, this algorithm also provides some value, which is referred to as tag, because when the person who performs the decryption will switch these places, but they will also obtain a tag value at the end, and they will check if it matches the one that you received through this insecure channel. If it doesn't match, this means that somebody modified the transmission. So this also provides authentication. Okay. So let's move on to FaceTel, and I will show this as an example and finish this part. So in this scenario, we divide the part as left and right. Okay, so you have plain text here, and you divide it into left and right. So the right part actually becomes left in the next round. But right part is also fed into a round function. In this round function, we have key addition part, substitution diffusion layers, then XOR it with the left part, and this part now is modified and becomes the right part. So in every round, you modify half of the input and obtain the ciphertext. The good thing is that encryption and decryption are almost identical, because you don't need the reverse of this round function. Because, for instance, assume that you get the ciphertext and you want to obtain plaintext, right? You have the secret key. So you don't, start from here and go in the reverse order against these arrows, because you already know the left and right part. So you put the right part to the round function and XOR it and obtain the value here. So encryption and decryption only changes the order of round keys. So in this part, you start from round key 1 to maybe round key n. In the decryption, you start with round key n and go to round key 1. It's as simple as that. Okay, we need to talk about this because some people still think that it is secure because the name says standard, right? So until a few years ago, even at the Microsoft web page, when you look at the encryption, they gave example as how you encrypt data with this. So I hope they removed it in 2023. But a lot of people still think that this is secure because they think that you cannot break it, even though it is a short key. They think that nobody will be able to perform brute force attacks on 56 bits. Okay. So it is designed by IBM in 1970s, based on earlier design by FaceTel, and in 1976, NSA tweaked the algorithm by changing its S boxes, also reducing the key length. So IBM at that time were using key length as 128 bits. So NSA reduced it so that they can perform brute force attacks. But they also tweaked the S boxes, which make the algorithm stronger, because at that time NSA knew the differential cryptanalysis technique, but IBM people didn't, so this is why they strengthened the algorithm. Currently, this algorithm is known as data encryption algorithm instead of standard, because people still think that it is a standard. It became useless after 1990s, since its short key is susceptible to brute force attacks. Again, people should stop using it in the 1990s, but I still hear people using it. So let me briefly explain the NSA involvements. NSA tweaked IBM's initial design by changing DES S-boxes, but they didn't explain IBM why they made such a change. IBM people analyzed this tweak and they discovered an attack that breaks the initial design. They called it T-attack. They shared their discovery with NSA. And NSA asked them not to share this knowledge with public, for they had known this attack for some time and were using it to listen to other countries. Biham and Shamir's rediscovery of differential cryptanalysis in 1990s is the first public announcement of this technique. Main idea in differential cryptanalysis is to find weakness so that a small change in the input provides an anticipated change in the output with high probability. Okay. So this is the picture. I'm not going into much detail. As you can see, you have the key schedule algorithm. You put the key, obtain some round keys. You have the right and left part. Right part is first expanded. So since this is 64 bits, these lines actually represent 32 bits. You expand it to 48, perform round key, then perform some S-box and permutation operations. And this part, which I call the round function, now I'm going to show the picture of it. It is like this. Okay. You expand 32 bits, right part to 48, XOR it with the 48-bit round key, then perform S-box operations, which takes 6-bit input and provides 4-bit output, then perform a permutation. Okay. So if you're interested, you can implement it. Here's a test vector. So if you take the plain text like this and choose the secret key like this, then your round keys will be these and round outputs will be this. So the end, it will be your cipher text block. This is important because it is generally not possible to implement a cipher in your first trial. So you need some test vectors to check if it is really correct. Okay. So security of DES, again, I said that this is broken because in 1992, Biham and Shamir provided the first theoretical attack using differential cryptanalysis, but since NSA strengthened the S-boxes, Biham and Shamir's attack required 2 to the 47 chosen plain text, which is not that realistic in practice. But if NSA didn't strengthen the S-boxes, then this attack would be practical. Matsui then provided first experimental cryptanalysis of DES by introducing linear cryptanalysis. So in a different project, DES shell project, out of computers connected by the internet break a message that is encrypted with DES. And there's also a machine called DES Cracker, which contains around 2,000 custom chips that can actually break DES key in 56 hours. As you can see, it is in 1998. And so this is only allowed in legacy systems. So people moved on to triple DES, where you use the DES 3 times consecutively. And since 2002, actually, advanced encryption standard became active, so people should use it after that part. So people try to strengthen the DES. Let me go in detail. So they said that if you use double DES, then the secret key will be 112 bits, so we will be secure. But actually, you can perform it half by half, so actually it provides 57-bit security. So, but if you use DES 3 times consecutively, where you choose to perform it as encryption, decryption, encryption, and choose the keys identical, it provides backward compatibility because it turns into DES. So I'm moving on to this, but many credit cards in Turkey uses triple DES, so it's still used. So what should be the key size, right? So if you try every key one by one, you need to perform 2 to the k operations, right? So this is called time complexity. So if you have DES, this is the number of keys you need to try. If you are using present with 80-bit key, this is the number. But if you move on to AES with 128 bits, as you can see, it increases exponentially. And this number is really huge. It is around the number of atoms that you can see, in the visible part of the universe. So, and to perform the brute force, you can use CPUs or GPUs, which are a lot faster in parallel algorithms. You can use FPGAs and then burn it to the silicon, those optimizations, and obtain an ASICs, which are dedicated hardwares. So let me show some numbers. For DES or triple DES on GPUs, we can try this many keys in a second. Okay. For present, this number is smaller because it has a lot of runs, so our optimizations weren't that good. But for AES, we obtained the best optimizations, and this is now can be considered as an old GPU, but if you use with something like 4090, this number will be a lot higher. But as you can see, we can try this many keys in a second, so this wouldn't be a problem. I mean, if you use 128 bits, it would be secure.